Swayam Prabha. Digital India. Educated India.
Hi everyone. In the last class, we have discussed the existence of the adjoint of a boundary linear transformation, and we also have observed that it is exactly a generalization of the adjoint of a matrix. Today, we are going to look at a few examples of adjoint of an operator and how to compute the adjoint. Okay, so let us first start with a simple example that we have already seen. If let us start with a bounded sequence lambda n. Define t from L2 to L2 by t of x1, x2, x3, so on, map to lambda 1 x1, lambda 2 x2, lambda 3 x3, so on. And we have shown that this is a boundary linear operator and norm of t as supremum of mod lambda n for n in n, that is subnorm of lambda n. And to find the adjoint of t, so we have to look at inner product tx with y and try to write that as inner product of x with some other element. Okay, so let us start with x equal to xn and y equal to yn in L2. And if you look at inner product tx with y, that is nothing but inner product of lambda 1 x1, lambda 2 x2, lambda 3 x3, so on, with y1, y2, y3, so on. So this can be written as summation j equal to 1 to infinity lambda j xj yj bar. Again this can be written as summation j equal to 1 to infinity xj multiplied by lambda j bar yj bar whole bar. So this is nothing but inner product x1, x2, x3, so on with lambda 1 bar y1, lambda 2 bar y2, comma lambda 3 bar y3, so on. So that gives us the inner product x with t star y. Hence we can conclude that t star of y1, y2, y3, so on is nothing but lambda 1 bar y1, lambda 2 bar y2, lambda 3 bar y3, so on for every yn in L2. So this is the adjoint of the given operator t. Okay, now let us look at one more example, which is exactly a generalization of the earlier example. Let us fix phi in L infinity of AB, that is the essentially bounded function. Define m phi from L to AB to L to AB by m phi at f equal to phi f, where phi f is nothing but phi f at t is phi t into f of t for every t in AB. We know that this is a boundary linear operator and norm of m phi is nothing but essential supremum of phi. We want to find what is m phi star, what is adjoint of m phi. So for this let us look at fg in L to AB, then we can consider inner product of m phi at f with g. By definition this is inner product from integral a to b phi t ft multiply gt bar dt, and that we can write as integral a to b f of t multiplied by phi of t bar g of t whole bar dt, and this is nothing but inner product of f with some element h, where h is nothing but phi of t bar gt whole bar. So we get this as inner product f with m phi bar g, where m phi bar is the multiplication operator induced by phi bar. Hence we can conclude that m phi star equal to m of phi bar, where phi bar of t equal to phi of t whole bar for every t in AB. So here f and g are arbitrary elements of L to AB. Hence inner product of m phi f at g equal to inner product f with m phi bar g for every f and g gives us that m phi star is m phi bar. Okay, so this is an example which generalizes the earlier example. And let us look at one more important operator, namely the Fredholm operator. So let us start with AB in R with A strictly less than B. Let us take a two variable function, that is k of st in L to AB cross AB, that is integral a to b mod k st square ds dt is finite. Now using this function, two variable function, we want to define an operator k from L to AB to L to AB by kf at s is integral a to b k of st f of t dt. Now first of all we have to show that this kfs is a function in L to AB. Then we can conclude that k is a well defined operator. Now for almost all t we can conclude that kst ft is a Lebesgue measurable function. Now we want to show that it's also L2 function. So that means we want to look at what is norm of kf, L2 norm of kf. So if you look at that, by definition, that is integral a to b mod kf square ds whole power half. So for this reason, let us try to look at this part, that is mod kfs. So if you look at mod kfs by definition of the operator kf, it is modulus integral a to b kst ft dt. By the property of the integral, this is less than or equal to integral of the modulus, that is this is less than or equal to integral a to b modulus of kst ft dt. Now using the Holder's inequality, we can conclude that by the Holder's inequality we can conclude that integral a to b mod kst ft dt less than or equal to integral a to b mod kst square dt whole power of multiplied by integral a to b mod ft square dt whole power of. So the second quantity is nothing but the square of the L2 norm of f. So from this calculation we can if you look at L2 norm of kf square, that is integral a to b mod kf square ds, that is less than or equal to, by the earlier inequality, integral a to b mod kst square dt, and now this ds is there multiplied by the constant norm of f L2 norm of f square. So from this we can conclude that norm kf square less than or equal to L2 norm of this two variable function multiplied by L2 norm of f square. Hence we can conclude that norm of kf less than or equal to the L2 norm of the function two variable function small k multiplied by norm f. So hence we can conclude that norm of k less than or equal to the norm of L2 norm of the two variable function that we have defined, which is an L2 function. So this function is known as the kernel function of the operator capital K. So most of the properties of K, the operator K, depends on this kernel function. Okay. Now we want to find what is the adjoint of K. So as usual, let us take Fg in L2AB and try to find inner product of Kf with G, and try to write this in terms of inner product of F with some element of L2. So let us try to look at inner product Kf with G. So that is nothing but integral a to b Kfs Gs bar ds. Now if you write what is Kfs, integral a to b Kst ft dt. So if you substitute that, inner product Kf with G is nothing but double integral a to b Kst ft dt Gs bar ds, and this is again double integral a to b Kst ft Gs bar dt ds. Now if we change the order of the integration by Fubini's theorem, we can say that this is nothing but integral a to b ft integral a to b Kst bar Gs ds whole bar dt. So this is nothing but inner product of f with k star g, where k star g is nothing but integral a to b Kst bar Gs ds. Okay. Now if you write s by t, if you replace s by t, or if you interchange the roles of s and t, then we get k star g at s is nothing but integral a to b k t s bar g t dt. So this k t s bar function we can write as a new function k star of st. So then we can get k star of g at s is nothing but integral a to b k star st gt dt, where k star st is nothing but kts. Okay, so the idea is that we were able to get adjoint of k again, which is an integral operator given by the kernel function k star of st, where k star of st is given in terms of k of ts bar. So it depends on k only. Now as a special case, let us take a equal to 0 and b equal to 1, and we define a new operator, Volterra integral operator. So we define k of st as 0 when 0 less than s less than t, and 1 when 0 less than t less than or equal to s. Now if you look at this diagram, so this is integral 0 to 1, sorry, this is from 0 to 1, and this also from 0 to 1, this s axis and t axis. When s equal to t, you will get this one, and when s less than or equal to t, then we will get the upper triangular, and when t less than or equal to s, we will get the lower triangular. Okay, so this operator, integral operator, is known as the Volterra integral operator. So it is denoted by Vf at s is nothing but integral 0 to 1 kst ft dt with this particular k. And if you substitute this k value, I mean value of the operator kernel k, you will get this as integral a to s ft dt. So that means from this we can, from the earlier example, we know that how to compute k star when k is given. So using this we can actually conclude that v star f at s is nothing but integral s to b f of t dt. So this is the adjoint of the Volterra integral operator, and we can easily show that as a particular case of the integral operator, this is also bounded, and it is bounded by the L2 norm of the kernel function. So here by using this definition we can find what is the L2 norm of the kernel function. Okay. Next we discuss one more important example, so that we will be using again and again. So let us look at L2 of z, that is two-sided sequences xn, where n is coming from z, such that summation n equal to minus infinity to infinity mod xn square is finite. That means the series is mod xn square, the series is absolutely convergent. You take x equal to xn and y equal to yn, and define the inner product of x with y as summation n equal to minus infinity to infinity xn yn bar. We can show that this is L2z is a Hilbert space with respect to this inner product. Now when x is in L2z, we have indices on the right hand side from 0. At 0 we have x naught, on the right hand side we have integers, positive integers 1 2 3, on the left hand side of 0 then we have minus 1 minus 2 minus 3 so on. So this is a two-sided infinite sequence starting at 0, and on the right hand side we call we have x1 x2 x3, on the left hand side of x0 we have x minus 1 x minus 2 x minus 3 so on. Okay, now when we write x as this way, the x0 is nothing but the index we call a 0th position of the two-sided sequence. Now we define an operator u from L to Z to L to Z such that the 0th position of the sequence xn goes to x minus 1. That means the 0th position is shifted to the component x minus 1. This is the 0th position here. So that means we are shifting one unit to the right hand side. So this is an infinite sequence shifted one unit to the right hand side. For that reason this is called bilateral right shift operator or the bilateral forward shift operator. So this is exactly similar to the bilateral right shift operator that we have defined on L to n, but only difference is that we have two-sided sequence here, components, I mean on from x0 you have right hand side indices, and the left hand side also we have indices input. So we can look at your norm of Ux(n) with respect to L2 norm, that you will get as norm of xn only. So from this we can conclude that U is bounded as well as norm of U equal to 1. We can easily check that this map is 1 1 as well as onto, whereas the right shift operator on L2, that's a 1 1 operator but not onto. Now we want to find what is the adjoint of U. So as usual, let us take x equal to xn and y equal to yn in L2z, and try to look at inner product x with y. So that is now if you look at the inner product, the zeroth position is at x minus 1. So this is the zeroth position, and here this is the zeroth position. Now if you multiply, you will get this sequence x, so on. This is what we get, and we want to write this as the sequence xn inner product with something. So here for xn we have the zeroth position at x0, and x0 is multiplied with y1 bar in this inner product. So we can this is nothing but inner product of xn with the sequence, the two-sided sequence whose zeroth position is y1, and on right hand side we have y2, y3, so on, and the left hand side of y1 we have y0, y minus 1, y minus 2, so on. So from this we can conclude that u star of y is nothing but a sequence whose zeroth position is at the index 1. So this is shifting one unit to the left hand side. So for this reason this operator is known as bilateral left shift operator or bilateral backward shift operator. So here also we can conclude that u star of the sequence yn is exactly norm of yn. So this operator is also both 1 1 and onto. So in the earlier case we have seen that the adjoint of the right shift operator is the left shift operator on L2, but we know that R is 1 1 but not onto. Similarly we can conclude about L also. So L we will not get an isometry, that is L of y1 yn you will not get norm yn. Okay, so now we want to discuss about the matrix of an operator. So we have seen that if the operator is given by a 2 by 2 matrix ABCD, the adjoint of the operator is given by the adjoint of the matrix ABCD. Now what is a matrix of an operator? So suppose we have a separable Hilbert space H with an orthogonal basis E1, E2, E3, so on, and if T is a bounded linear operator from H to H, then the matrix of the operator T is given with respect to this basis B is given by as follows. It's an infinite by infinite matrix A whose ijth position is Aij, ijth entry is Aij. Now Aij is nothing but inner product of Tej with Ei. So with respect to the orthogonal basis B, the matrix of T is given by this infinite by infinite matrix A11, A12, A13, so on. Second row is A21, A22, A23. Similarly, nth row is given by an1, an2, so on, ann. So this is an infinite by infinite matrix. For example, if you look at the right shift operator on L2, so this sends R of En into En plus 1. So where En is 0, 0, 0, this is in the nth position. So E1 is mapped to E2 and E2 is mapped to E3. So for this reason we can actually get the matrix of R with respect to this standard orthogonal basis. So the first column is E2 0 1 0 0 so on. Second column is E3 0 0 1 0. Like this, if you continue, you will get the matrix of R is obtained in this way. Similarly, we know if you look at the adjoint of this, we will give the matrix of the right shift operator. So the matrix of L with respect to the standard orthonormal basis is exactly 0 1 0 0 0 0 1 0 0 0 0 1. So this is the main diagonal, and we get all ones immediately after the main diagonal, above the main diagonal. Whereas in the earlier case, this is the main diagonal, and you will get the next subdiagonal down the main diagonal, you will get all ones. So that is for the right shift operator, and this is for the left shift operator. So you can check find the matrix of U and U star, where the U is the bilateral shift. Bilateral shift on L to Z. So with respect to the standard orthonormal basis, En n in Z. So here En at M is given by 1 when n equal to M, 0 n not equal to. This is the orthonormal basis element En. Okay. So this is about finding the adjoint of an operator and how to find the matrix of an operator. Now suppose T is a bounded operator. Let T be a bounded operator defined on H, and now we want to see, suppose Bij be the matrix of T, matrix of T star with respect to the orthonormal basis E1, E2, so on. Now we want to find the relation between Bij and Aij, the matrix of T with respect to the same basis. So let Aij be the matrix of T with respect to the orthonormal basis E1, E2, so on. Now Bij is nothing but inner product T star Ej Ei for all Ij, and now by the relation between T and T star, we can write this as inner product Ej with Tei, and this again can be written as inner product Tei Ej bar, but this is nothing but jth element of the matrix T, matrix of T and its bar. So this is a relation between the matrix of T star with the matrix of T. So in other words, if you look at T star with respect to the same basis, this is nothing but, so earlier it was A11, A12, so on. Now this is A11 bar, A21 bar, this is A12 bar, A22 bar, A32 bar, so on. So this is exactly adjoint of the matrix of T. So this is the relation between the matrix of T and T star. Okay. Now let us come back to the property of B of H1 H2. We have shown that, recall, B of H1 H2 plus and dot, this is a vector space, and we have defined the operator norm. So when T is in B of H1 H2, this implies norm of T is a finite quantity defined by supreme of norm Tx, where x is coming from H1 with norm x equal to 1. This is the norm of T. Now we can ask the question that if you put this norm, can we say that this is a nonlinear space? A non-linear space. That means the first thing we have to observe is that if this is true, can we say that T is 0 operator? That can be easily done. If norm T is 0, this is norm of Tx is 0 for every x in H1 with, in fact, when x is non-zero, we can replace x by norm x and we can conclude that this is norm of Tx is 0 for every x in H1. This implies T equal to 0. Note that here 0 means it's a map from H1 into H2. Every element of H1 is mapped to 0 element of H2. Then this is a 0 map here. Otherwise trivial. When T is a 0 map, then norm is, so we can conclude that part. And what can you say about norm T plus S? Norm T plus S, where S is another bounded operator. So let us take then we can conclude that we can find out what the norm of T is. Let us take ST from B of H1 H2, then norm of S plus T at X. We can show that S plus T is a bounded operator. That is easy. By taking the sequences, we can prove it easily. Now this is less than or equal to, this is so let me repeat here. Let us take str2 bounded operator from H1 into H2. Then by definition of the boundedness or continuity of operators, we can show that S plus T is a norm. So we can find the norm of T norm of t plus s by the definition of the norm. This is supreme of norm of sx plus tx, where x is coming from h1 and x non-zero. So we know that sx plus tx is less than norm sx plus norm tx by the triangle inequality, because sx and tx are vectors in H2. This is again norm s into norm x plus norm t multiplied by norm x. So this is norm of s plus norm of t and norm of x1. So hence we can conclude that norm of s plus t, you take supremum right hand side, supremum norm x equal to 1, then right hand side it is norm s plus norm t, and left hand side is norm of s plus t. This is norm s plus norm t. So the triangle inequality for the norm is satisfied. Now the other property, if lambda is a complex number and t is a bounded operator, then we can easily show that norm of lambda t is mod lambda norm t. So the conclusion is that B of H1 H2 with respect to the operator norm is a non-linear space. So B of H1 H2 plus dot this operator norm is a non-linear space. Now when you take H1 equal to H2 equal to H, we are denoting that by B of H. So let us take, we know that B of H with plus dot and composition is an algebra. Now we want to show that how the composition of two operators, how the norm of the composition of two operators is related with norm of the individual operators. Let us take s and t to be two bounded operator on H. Then by definition, norm of s composition t, this is supremum of norm of s of tx, where x is coming from H1 with norm x equal to 1. Now we know that norm of stx is less than or equal to norm s into norm tx for every x in H1, and now this is less than norm s into norm t into norm x, because norm tx is less than or equal to norm t multiplied by norm x for every x in H1. So from this, therefore we can say that norm of st is less than norm s multiplied by norm of t. Okay, so we can with this operation we can conclude more about this B of H. So B of conclusion, B of H with plus scalar multiplication, composition and this operator norm is a normed algebra. So in general, what is a normed algebra? Definition: an algebra A is called a normed algebra if there exists a norm from A into R such that norm of A composition B less than or equal to norm A, norm B for every A, B in B. Here A circle B or A composition B. This is a multiplication in A, so it need not be composition all the time, but it's a operation which we denote it by circle. Most of the time we don't use this circle. Instead of A composition A circle B, we write it AB. So no notational convenience. So we write AB instead of A circle B all the time for convenience only. Okay, so now we know that we are defining a new function, namely the norm, and norm actually connects vector space structure already, which is there. Now this AB is a multiplication in A, so this condition which we have given here connects the multiplication of elements in A with the norm. So such a norm we call as the algebra norm. So this is called algebra norm. So in algebra, with a algebra norm, we call it a normed algebra. So now we can give a better example, that example BH with plus dot circle and the operator norm is a normed algebra. If the norm is complete norm, we call that an algebra to be Banach algebra. So definition: a complete normed algebra is called a Banach algebra. So another example, the same example, B of H is a Banach algebra plus dot circle is a Banach algebra. Because we know that B of xy is complete with the operator norm if and only if y is complete. This is a well-known result from function analysis. So here when we say B of xy, it is the operator norm B of xy, where x and y are nonlinear space. This is the operator norm. This is complete if and only if y is complete. Now we know that x equal to y equal to h, which is a complete space. Hence B of h, that is B of h, is complete with respect to the operator norm. Hence this is a Banach algebra. Okay, now so far we have discussed about properties of norm, properties of operator norm. Now we also want to check how this operator norm behaves with the adjoint operation. So before doing that, let us look at some important properties of adjoint. So we have defined a map from B of h into, in fact we have defined from B of h1 h2 into B of h2 to h1 t going to its adjoint. We have shown that whenever t is bounded, t star is also bounded with the same norm as t. So we have shown norm of t equal to norm of t star, and the second property we have noted is that t double star is exactly t. Okay, now we want to see how the star operation behaves with the addition of two operators and composition of two operators. Okay, now if you take alpha a complex number and t star, we can say that alpha bar t star. This can be proved easily. Now s plus t star, we can easily show that s star plus t star. So the proof is easy. Let us take x is in h1 and y is in h2. Then we want to look at s plus t star. How to compute that? Let us look at s plus t x inner product with y. This is sx inner product with y plus tx inner product with y, but we know that this is x inner product s star y. And this is inner product x with t star y. So this is nothing but inner product of x with s star plus t star y. But we know from the left hand side that actually represent x s inner product with s plus t star y. So from this we can conclude that s plus t whole star is s star plus t star. Okay, so this is on h1, but we cannot discuss product here. So let us take h1 equal to h2 equal to h and st in b of h, and we want to see what is st whole star. So for x, y in h, you want to find what is inner product of, what is adjoint of st. So st x inner product with y, this is what we want to show. So this is nothing but inner product tx. When you take s other side, it becomes s star y. Again when you take t to the other side, this inner product of x with t star s star y. Okay, from this we can conclude that inner product of x with st whole star of y is nothing but inner product of x with t star s star y. This is for every x, y in h. From this we can say that st whole star at y equal to t star s star acting on y. So that means for every y. So this shows that st star is t star s star. Okay. Now the one can ask the question that what is a adjoint of identity. If you look at any scalar lambda, so we can easily check that lambda identity star is lambda bar identity, where identity is a bounded operator on h, taking x going to x itself. Okay, now we know that BH is a BH with respect to the operator norm is a Banach algebra. Now with respect to this operation, we can call this as a Banach star algebra. So before defining Banach star algebra, let me define what is a star algebra. So definition: an algebra A is called a star algebra if there exists a map which we denoted by star from A to A satisfying the following axioms. A double star is A, that means this is called involution. A plus B whole star is A star plus B star, and AB star, here AB means product of A and B. So instead of writing A circle B, we are writing AB. This is B star, A star, and lambda A star is lambda bar A star, 1 star equal to 1. So if 1 belongs to A, if A is unital, we can conclude that 1 star equal to 1. So such an algebra we call as a star algebra, and if there is a norm, we want to see how the norm is connected with the involution. Okay, so next definition, a Banach star algebra A is called a C star algebra if norm of A star A is exactly norm A square for every A in A. So this condition is known as the C star condition. Now the question we can ask is that, is BH a C star algebra? So with the earlier operations, earlier properties of star or adjoint, we can conclude that it's a Banach star algebra. Now we want to check whether BH satisfy the C star condition or not. So let us take T is in B of H. Then we want to see whether norm T star T is exactly norm T square or not. Then norm T star T is less than or equal to norm T star multiplied by norm T, because we have shown that norm of ST less than norm S into norm T, but we know that norm T star and norm T are same, so we can say that therefore we can say that norm T star T. Now we want to check whether the other way inequality is true or not. So for that, let us take x is in H, then norm of Tx square, we can write inner product Tx with Tx, and we can say this is we can take T to the right hand side, to the right hand component. This will be x T star Tx, and by the Cauchy-Squarge inequality, this is less than norm x into norm of T star Tx. But T star T is a bounded operator, because we know that whenever S and T are bounded operator, ST is bounded operator, and norm of ST less than norm S into norm T. So we can say that this is norm T star T multiplied by norm x, and already norm x is there, so this will be norm x square. So taking supremum on the both sides over norm x equal to 1, we can conclude that norm T square is less than norm T star T. So let us say this is 1 and this is 2. So from 1 and 2 we can conclude that norm of T star T is exactly norm T square. Hence we can conclude that BH with plus dot circle operator norm and the involution, and so these are the operations. This operator norm itself is a C star norm. It starts with a C star condition. So this is a C star algebra. So we look at only complex C star algebra because we are looking at BH as a complex vector space. So this is a complex C star algebra. So most of the time, instead of specifying all these operations, we say that BH is a C star algebra. Okay, now the question arises, what are all the other C star algebras? Can we give examples of other C star algebras? Let us look at one more example. Let us take K to be compact Hausdorff space and look at A to be C of K, the space of all continuous functions defined on K and taking values in C. Set of all F from K to C. F is continuous on K. Okay, we know that C of K is a vector space. If you define F plus G, HT as Ft plus Gt, alpha F, it is alpha T, alpha F of T, alpha in C, and T is in K, and the circle. Here the multiplication we define as a pointwise multiplication, so we will not write a circle because circle is used for composition. This is the multiplication in the algebra. So we have observed that with respect to all these operations, we have shown that this is an algebra and the norm is the supreme norm, supreme of mod F of T, where T is coming from K. So we know that with respect to this subnorm, C of K is a Banach space. Now we define F star of T as F of T bar for every T in K. With respect to this operation, it becomes a star Banach star algebra, and in fact this satisfies the C star condition. So we can say that C of K is a C star algebra. So A is a, in fact, unital commutative C star algebra. In fact, we can show that if there is a abstract unital commutative C star algebra, then that can be identified with C of K for some K. So that is nothing but Gelfand-Neumann theorem. If A is a commutative unital C star algebra, then A can be identified with C of K for some compact Hausdorff space. So this is known as the Gelfand-Neumann theorem. So what is a way of identifying? So here the identification means all the properties, all the operations of the C star algebra are preserved. Such a map we call as a star representation. It preserves all the structures of C star algebra. For example, it is linear. It preserves the norm, isometry. It's also onto, and it preserves the adjoint. So there exists pi from A into C of K such that pi is linear then pi preserves the multiplicative structure phi of A, the norm is preserved and pi is onto pi of A star is pi of A whole star for every A in A, and pi of 1A, that is the unit element in A, is nothing but the constant function. The unit element in C of K, that is constant function. So it preserves all the C-star algebra properties. Such a map we call as star representation. Okay, so up to such identification, there is only one unital commutative C-star algebra, that is C of K. Okay, this is a commutative version. Non-commutative version is the non-commutative version of Gelfand-Naimark theorem is nothing but the Gelfand-Naimark-Segal theorem, which says that any C-star algebra can be embedded as a C-star subalgebra of B of H. So this the GNS theorem, Gelfand-Naimark-Segal theorem. This says that if A is a unital C-star algebra, then there exists a Hilbert space H such that A can be identified as C-star subalgebra of B of H. B of H is a concrete C-star algebra, and any abstract C-star algebra can be identified as a C-star subalgebra of B of H for some Hilbert space H. So this is called the Gelfand-Naimark-Segal theorem. From this point of view, these are the only two examples of C-star algebras, commutative as well as non-commutative. So these proofs we will not be looking at, but these are most useful results in other areas of mathematics. Okay, so with this I will stop here. In the next class we will be discussing about some special class of linear operators which are defined based on the adjoint of an operator. So we will be discussed in the next class. Thank you very much.